All right, welcome to The Explainer. We're about to open the case file on, honestly, one of the biggest mysteries in all of science. We're talking about a strange, invisible force that's literally pushing our entire universe apart. This is the unsolved case of dark energy. So every good detective story, right? It needs a crime scene. And that's exactly where we're going to start, by setting the stage for our cosmic investigation. You see, for the longest time, we were pretty sure we knew the number one rule of the cosmos. And that rule? Super simple. Gravity is king. I mean, ever since Edwin Hubble figured out the universe was expanding, the big assumption was that all the stuff in it, all that matter, its gravity had to be acting like a giant cosmic brake. It had to be, right? Everything we knew, from Newton all the way to Einstein, told us that the gravitational pull between all the galaxies and stars had to be slowing that expansion down over billions of years. This wasn't just some wild guess. This was the absolute bedrock of cosmology. But then, 1998. Two separate teams of astronomers are looking at these really distant exploding stars, and they find something that just completely shatters that whole idea. I mean, they were expecting to see the universe tapping the brakes. Instead, it was like someone floored the accelerator. The expansion of the universe isn't slowing down at all, it's speeding up. So, you gotta ask, how could they be so sure? A claim that huge, that radical, it needs some seriously rock-solid evidence. So let's follow the clues. Let's see what the detectives of the cosmos actually found. Well, the first big clue is kind of like a cosmic census. When scientists add up everything we can actually see, stars, galaxies, gas, the whole shebang, it only accounts for about 5% of what should be there. And okay, even when you throw in all that mysterious dark matter, we're still missing a whopping 68%. This missing stuff, what we call dark energy, isn't some minor detail. It's running the entire show. And look, this wasn't just based on one thing. The case is built on 4 totally independent lines of evidence, and they all point to the exact same culprit. So first up, you've got those supernovae that started it all. They were dimmer, which means they were farther away than they had any right to be. Then there's the afterglow of the Big Bang, the cosmic microwave background. The CMB tells us our universe is flat, geometrically speaking, and that math only works out if this extra energy is part of the equation. Third, we have these ancient ripples in space called baryon acoustic oscillations, or BAOs. Think of them as a cosmic measuring stick that confirms the universe is accelerating. And finally, the way huge galaxy clusters grow over time, it's being slowed down, almost like gravity is fighting and losing a battle against this invisible push. Okay, so you've got your crime scene, you've got solid evidence. What's next? Well, the cosmic detectives needed a name for their prime suspect. And they called it dark energy. Its defining feature is this really weird, kind of mind-bending concept called negative pressure. Here's a way to think about it. Normal pressure is like the air inside a balloon pushing it out. But negative pressure, that's like the fabric of the balloon itself wanting to expand, stretching everything inside it further and further apart. It's a repulsive force that's just built into the very fabric of space-time. So what is this stuff? I mean, what could possibly be powerful enough to overwhelm the gravity of the entire universe? It's a huge question. And physicists have lined up a few prime suspects. Believe it or not, the lead suspect is actually an old idea from Einstein himself. He came up with something called the cosmological constant to basically force his equations to show a universe that was static, not expanding or contracting. When he found out the universe was expanding, he famously called it his greatest blunder. But here's the stunning twist. It turns out Einstein's biggest mistake might just be our best clue, because what it describes is an energy that's just part of space itself, which is a perfect match for dark energy. Okay, but here's where things get really wild. The cosmological constant fits what we observe perfectly, but it creates this massive theoretical problem. You see, our other great pillar of physics, quantum field theory, can actually predict how much energy empty space should have. The problem? The number it spits out is 10 to the 120th power, bigger than what we actually see. That's a 1 followed by 120 zeros. It's so wrong it's famously been called the worst prediction in the entire history of physics. No exaggeration. So this gigantic mismatch leaves us with a lineup of very different suspects. First, you have the cosmological constant. It fits the evidence, but we have absolutely no idea why it has the value it does. Then there's an idea called quintessence, which is some kind of hypothetical energy field that might change over time. And then you've got the most radical idea of all. Maybe there's no dark energy. Maybe our understanding of gravity itself, Einstein's general relativity, is just incomplete on these huge cosmic scales.
So which one is it? Which theory is correct? The honest answer is we just don't know. The case is still wide open. And figuring this out isn't just some academic puzzle. The answer is going to decide the ultimate fate of our entire universe.
Now, if the cosmological constant is the right answer, then we're headed for a future known as the Big Freeze. This relentless acceleration is just going to keep going, pushing all the distant galaxies so far away that we'll never see them again. Our local group of galaxies will be like a lonely island in an endless, empty void. Eventually, star formation will stop, the last stars will flicker and die, and after an amount of time that is just unimaginable, even the black holes will evaporate, leaving behind a universe that is completely cold, dark, and empty. So yeah, the Big Freeze is definitely the current frontrunner, but other, even more dramatic endings are still possible, all depending on what dark energy really is. For example, if it turns out to be a phantom energy that actually gets stronger over time, it could lead to something called the Big Rip, where it violently tears apart everything, galaxies, stars, planets, right down to the atoms themselves. And the opposite idea, the Big Crunch, where gravity finally wins and pulls everything back together, well, that one seems to be pretty much ruled out by the data we have now.
And this is exactly why this all matters so much. The investigation is nowhere near over. In fact, a whole new generation of incredibly powerful telescopes, we're talking the Vera Rubin Observatory, the Euclid Space Telescope, and the Nancy Grace Roman Space Telescope, they are specifically designed to hunt for more clues. Their mission is to map billions of galaxies with insane precision, all in the hope of finding that one crucial piece of evidence that will finally crack this cosmic case once and for all. And so that leaves us with the one final tantalizing question that really drives all of this research. Is dark energy just a fixed, unchanging property of space, sealing our fate in that long, cold, big freeze? Or is it something dynamic, something that could change over time, leaving the final chapter of our universe still unwritten? The answer is out there, somewhere, just waiting to be discovered.